Chapter 1 Real Numbers.
Prove that 6 raised to n cannot end with a digit 5 in the unit place for any natural number value for n. Okay, so this similar question is proved in the textbook. One of the example solving problem is almost similar. I think 4 raised to n something. Okay, so here you can give the similar proof. Here you know the prime factorization of 6 is what is prime factorization of 6?
2 into 3.
2 into 3. Prime factorization of 6 is 2 into 3. And you want to mention by uniqueness property of fundamental theorem of arithmetic, there is no other way 6 can be prime factorized. Only in this way we can write up a prime factorization of 6. Okay, so there is no other chance. So 6 raised to n will be 2 into 3 raised to n. So that will be 2 raised to n into 3 raised to n. This shows that in the prime factorization of 6 raised to n, there will be only 2 primes, 2 and 3. There will be no other prime. But we know if a number ends with 5, if some number ends with 5, then that number will be divisible by 5, or 5 will be factor of that number. 5 is a prime number. If a number is a factor of a given number, then if that is a prime number, then that number will occur in its prime factorization. Okay, but here in prime factorization of 6 raised to n, there cannot be 5 because of this uniqueness property of fundamental theorem of arithmetic. So it is not possible for 6 raised to n to end with 5. That's a proof. You want to write with the sentence. Okay, so some other way we can say like this. Prime factorization of 6 is 2 into 3. Okay, and you know, if a number ends with 5, so if a number ends with 5, then that number will be an odd number. If a number ends with 5, that number will be odd number, because unit or the digit in the unit place is 5, odd. Okay, so the number will be odd number. But 6 raised to n, the prime factorization of 6 is 2 into 3. By the uniqueness property of fundamental theorem of mathematics, there is no other chance to prime factorize 6. Okay, so 6 raised to n will be only the form will be 2 into 3 all raised to n. That will be 2 raised to n into 3 raised to n. Since 2 is a factor of 6 raised to n, that number 6 raised to n will be an even number. If 2 is a factor of a number, then that number should definitely be an even number. So 6 raised to n is an even number. The number ends with 5 is an odd number. So it cannot be, right? It is a contradiction. 5 cannot be in the units place because 6 raised to n is always even. Okay, so like this also you can give the proof. I think both are almost the same effort you want to take. Okay, and another one, root 5 plus root 3. So, root 15 is irrational is given. Root 15 is irrational is given, and to prove that root 5 plus root 3 is irrational. Okay, so using the given idea, you want to prove this. I think it was 2 mark question, 2 mark or 3 mark. I have some small confusion. Anyway, how to prove this? Root 5 plus root 3 is irrational. We want to prove the sum of 2 irrationals will be irrational. That was a wrong statement. A sum of 2 irrational need not be irrational always. So we cannot say sum of 2 irrational is always irrational. I will give some example. Suppose 10 plus root 2. 10 plus root 2. As considering a single number, 10 plus root 2, sum of these two numbers will be a single number. As considering this sum as a single number and 10 minus root 2 as this difference as a single number, if you add these two, that means adding two irrational numbers. So that time root 2 and root 2 will be cancelled, you will get 20. So that means irrational plus irrational is rational. Irrational plus irrational is rational. This is also not always, but in some case rational. Most of the case the sum will be irrational itself. Irrational plus irrational will be irrational itself. But in some case like this, the sum may be rational number. So we cannot say irrational plus irrational is equal to irrational. Please note it. We cannot say this. Not always. Okay. So here how we can prove is we want to use the given idea. Root 15 is irrational. So the idea is you first take the given number. This is what we want to prove that rational. So let us assume that this is rational. This is rational. Then we can write this as a by b, or a and b are co-prime numbers. Okay. Then taking square on both sides. Taking square on both sides, you will get to, you can apply the identity in the left side. So what is a plus b whole square? You know the identity, right? That identity you apply in the left side, you will get a root 5 square. Root 5 square will become 5 plus 2 into root 5 into root 3. 2 into root 5 into root 3 plus root 3 square. Root 3 square will become 3. And a by b all square will become a square by b square. Okay. And here 5 plus 3 will become 8. So 8 plus 2 root 5 into root 3 is equal to a square by b square. You're moving 8 to right side, it will become minus 8. And then move this into 2, that will become divided by. Okay, so in left side, root 5 into root 3 will become a square by b square minus 8 into 1 by 2. So root 5 into root 3, how we can write root 5 into root 3? So
root 15.
Yes, root of 5 into 3, you can write like this, root of 5 into 3. What is root of 5 into 3? That is 15, right? So this shows that here RHS of this equation will be a rational number, right? Because A is rational, B is rational. Okay? So a square by b square will be rational. Subtracting a rational from a rational will be again rational, and dividing it again by rational will be again rational. So RHS is rational, so the LHS must be rational. But given that root 15 is irrational, so this is a contradiction. So this contradiction arises because of our wrong assumption that root 5 plus root 3 is rational. So we conclude that root 5 plus root 3 is irrational. That's a proof. Please note some of properties here. Sum of two rationals. Is it always rational? Sum of two rational numbers?
Yes.
Yes, right. Difference and product
Will be rational.
Yes, yes. The sum of two rationals will be always rational. Difference will be always rational, and product will be always rational. And if you divide a rational by another rational, the quotient will be rational.
But in this case, denominator cannot be 0.
Okay. What about if we take one rational and one irrational and add?
Irrational.
Irrational. Okay. This is true always. Sum of a rational and irrational will be always irrational. And the difference of a rational and irrational, and the product of a rational and irrational, and dividing a rational by irrational, what will come?
Always irrational.
Oh, yes. All is irrational.
But here for multiplication and division, R cannot be 0. If R is equal to 0, then we will get a rational, right? So rational into irrational is irrational except for R is equal to 0. Same way, rational divided by irrational is irrational except for R is equal to 0.
Okay, and if both are irrational, if you do these four operations, the answer can be rational or irrational. Two chances are there. Sometimes it may be rational or irrational for addition and subtraction, multiplication, division also.